Hi everybody, hope you are amazing today. We are going to start chapter 18 today, and chapter 18 encompasses a whole bunch of stuff. It has reaction rates, reversible reactions, equilibrium, and spontaneity. So we are going to start with spontaneity today. And so what is spontaneity? What does it mean? A spontaneous reaction means that it's a reaction that will occur on its own without outside intervention. So it is a reaction that is favored to happen by nature and will occur by nature without outside intervention. Now, that's not to say you don't need to give it a little push, little activation energy to get it to go. That does not mean it's not spontaneous on its own. It also does not mean that it's going to happen fast. So some spontaneous reaction actually take a very long time to occur. So for example, if you look at this picture here, if I'm trying to roll the ball to get it to go uphill, that's not really a spontaneous reaction. I've got to put in a lot of outside force, an extreme amount of force, to get this to go up the hill. Nature would prefer it to not go up the hill. So that would be non-spontaneous, not preferred by nature, which means it can occur, but it needs a very strong outside intervention, outside force to get it to go. Whereas if the ball is at the top of the hill, that is a spontaneous reaction to get it to go down. Now, it might sit there for a long time without falling. It might need me to give it a tiny little push to get it to go. That would be like your activation energy. But the natural thing for it to occur, nature would prefer it to go down the hill. So that would be a spontaneous process. So, in order for a reaction to be spontaneous, to actually occur, which really means that, if I have a reaction, so I have reactants turning into products, right? Well, in reality, most reactions are reversible, which means once you form products, those products can then turn back into reactants. So it kind of goes back and forth. It's reversible, like a reversible jacket, right? So a spontaneous reaction means that it prefers to go this way. That at the end of the reaction, you're going to have more products than you would reactants. That the natural way for it to go is to the right, to go from reactants to products, as opposed to the other way from products to reactants. So a spontaneous reaction that will occur, that will happen, that will go forward, is decided by two factors or two driving forces. Two forces in nature that decide whether a reaction will be spontaneous or not. The first is enthalpy and the second is entropy. Those two words sound very, very similar. We have talked about enthalpy in the last chapter, and entropy is kind of new. So let's start with enthalpy here. And so enthalpy is the heat of the reaction, the energy that is transferred in a reaction. So you can call it enthalpy or energy. They kind of mean the same thing. And the symbol for energy or enthalpy is delta H. To get delta H out of your reaction, you take the potential energy of the products minus the potential energy of the reactants. Products minus reactants, or final minus initial. And that gives you your delta H. And we've kind of talked about exo and endothermic reactions and all that. Well, nature prefers things to be even. It prefers things to be distributed equally. It likes equality. And so, same for energy. Nature prefers the distribution of energy. It wants energy to not be concentrated in one area, but to be spread out everywhere. So, exothermic reactions, which have negative delta H's, are actually favored by nature, whereas endothermic reactions, which have a positive delta H, are not favored by nature. Let's talk about why that is. An exothermic reaction, you're taking energy from your system and releasing it to the surroundings. So you're taking energy from the system and spreading it out over all of your surroundings, which, again, spread of energy is good, that is favored. Endothermic reactions are not favored because you're taking energy from the surroundings and concentrating them into the system. and that's not a good thing to concentrate energy or really concentrate anything. So you don't want to take the energy from the surroundings, put them into one little spot, which is your system, which is not good. So again, exothermic, delta H is negative, is favored. Endothermic, positive, delta H is not favored. So I'm going to go ahead and write that down real quick. Just to summarize, delta H negative is favored, delta H positive not favored. Okay, so let's take a look at these reactions here and decide, are these favored in terms of enthalpy? So in terms of energy, is this reaction good to go? So let's take a look at this reaction. We're given 3NO2 plus H2O yields 2HNO3 plus NO, and delta H is negative 138 kilojoules. This would be favored. Yes, it is favored because that negative tells us it's exothermic, and exothermic is good. That is favored by nature. Letter B. N2 plus O2 yields 2NO. Delta H, positive 180 kilojoules. That one, not favored because your delta H is positive. That's endothermic. That's not good. Let's look at the next one. H2O liquid going to H2O gas. They don't give us delta H there, but let's think about this. We have solids having the lowest amount of energy, then liquids, then gases. So we're taking a liquid and turning into a gas. In order for a liquid to become a gas, the liquid has to absorb energy to become a gas, right? Absorb. So that would be endothermic. Remember, evaporation is an endothermic process, right? And so endothermic would not be favored. Endo, delta H positive, not favored. Okay, let's look at CO2 gas going to CO2 solid. So now we're taking the gas and turning it into solid. So in order for a gas to turn to solid, that gas has to give away some energy in order to become a solid. So that is exothermic, which would be favored. Last one, CAS, yielding Ca plus S. That one is not favored. Why is that? Oh, I'm sorry, that should say E, not two D's there. That's E. This is not favored, though. Why? Because you are breaking a bond here, and breaking a bond is endothermic. Now, most reactions, like let's look at this reaction, you are breaking bonds here, which takes energy, endothermic. You are forming bonds here, which releases energy, exothermic. So in a regular reaction, you're breaking some bonds, you're forming some bonds, you look at how much energy it takes, how much energy it releases, look at the net, and see if it's negative or positive. If you look at this, we're breaking a bond here, we're not making any bonds here. And so we're only breaking bonds, not forming any bonds here, and so breaking bonds would be endothermic, so that is not favored. All right, so that is enthalpy. Now let's look at this new word, entropy. Entropy is a measure of disorder or randomness. Now the real definition of entropy, the real scientific definition, if you ask like a physicist or something, it's a lot more complicated than that. There's microstates and degrees of freedom and all kinds of stuff. For our textbook and for the purposes of our class, this is fine to define it as disorder or measure of randomness. But just know, when you take higher level science classes, you will realize that the definition is a little bit more complicated than that. Now, the symbol for entropy is delta S. And just like delta H of the reaction is products minus reactants, delta S of the reaction is the entropy of the products, the disorder of the products, minus the disorder of the reactants. So, just like nature prefers the distribution of energy, nature also prefers the distribution of matter. So think about this. What if I tell you, hey, go to your room and I want you to make it a mess? Open your closets, put everything on the floor, open your drawers, put everything on the floor. How long would that take you? For some of you, probably a few seconds, maybe a few minutes. Now, what if I tell you, now that your room is messy, I want you to organize everything, put it in order? So you need to put everything back in your closets, everything back in your drawers, everything needs to be organized and neat. How long would that take you? A lot longer. It is much harder to organize than it is to make a mess. That's because nature likes it to be messy. Nature prefers disorder. The second law of thermodynamics says that in order for a process to happen, the entropy of the universe needs to be increasing. So, another example, if I have a vase sitting on a table, it is very easy to get that vase to break. With a tiny little push, I can get that vase to fall down and break into 1,000 pieces. However, if I tell you, take each of those little pieces and put them back together so that you can make one nice, neat vase that is ordered, that is much, much harder. Because, again, nature prefers disorder. It is much easier to make a mess and break it into 1,000 pieces than it is to put it back together. Another example, making a salad. Much easier to toss a salad together than it is to, after the salad is made, find all the pieces of tomatoes, put them together, all the pieces of cucumbers, put them together, and so on. And so nature prefers disorder and randomness. So we want to, as we progress in our reaction, go from order to disorder, to more randomness, to more entropy. So we want the products to have more disorder than the reactants. Now, if the products have more disorder than the reactants, then as you do S of products minus S of reactants to get delta S of the reaction, if we're saying more disorder or entropy in the products, then this number is bigger than this number, so your delta S of the reaction would be positive. So when your delta S is positive, that is favored. Now, if you're going the other way, if you're trying to clean your room and you're going to more order, that's not good. We don't want that. So if we're saying the products have less disorder, less randomness than what I start with, then this number is smaller than this number, which would make it negative, and that is not favored. So let's go to the next slide and look at some examples. And just to review, we said when delta S is positive, that is favored, which means from less to more disorder or randomness. That's good. If delta S is negative, that is not favored, which means we're going from more to less disorder. So our first example here, we have H2O liquid going to H2O gas. That process would be favored because gases are a lot more random than liquids are. So as you go from solids to liquids to gases, you are becoming more and more disordered, and that would be favorable. Going the other way, like from gas to liquid to solid, that would not be favored in terms of entropy. Okay, next one, CO2 gas to CO2 solid. That one is not favored. The reason is gases are more random than solids. Solids are in this nice ordered crystal with repeating patterns, right? That's very, very low entropy compared to this one, and so that would not be favored. How about this one? H2O gas plus H2O to liquid going to 2H2O liquid. That one is not favored. You're going from a combination of gas and liquid to all liquid. And so we're becoming more ordered, and that is not favored. Let's look at the next example. CaCl2 decomposing into calcium and chlorine. That one is favored. The reason is, this is like my example of the vase. So one big thing turning into two little things. That would be more messy or more disorder. And so that would be favored. So going from less particles to more particles mean you're going to more disorder, and that is favored. Let's look at this example. 3NO2 plus H2O yielding 2HNO3 and NO. That one, we're going from 4 particles to 3 particles. We're going from more to less particles. That's not good. We're going to more order, so that is not favored. So to review, we said nature prefers the spread of energy and of matter. So if we are spreading energy, that means that the products have lower energy than the reactants because we spread that energy out of our system to the surroundings, and that means that your reaction will be exothermic. Delta H is negative. For matter to spread, you want the products to have more disorder than the reactants, which means the reaction has a positive delta S. So let's think about what this means here. Again, to review, I'm going to write up here. Delta H, remember we said if it's exo, if it's negative, that is good. That's favored. Delta H is positive, not favored. Delta S is the opposite, right? Delta S, if it's positive, that is favored. Delta S, if it's negative, that is not favored. It's a little bit confusing because, they're kind of opposite of each other. So let's look at these different scenarios here. So if my delta H is negative, move this a little bit. Delta H is negative. Is that favored? Yes. That is good. I'm going to actually put a check mark instead of favored or not favored. So yes, that's a good thing. Reaction should go according to delta H. How about delta S? If delta S is positive, that is favorable. That's great. So this reaction is favored by both enthalpy and entropy. They're both saying this reaction should happen. That means reaction is always spontaneous. What does that mean? It means it will happen at any conditions. Now, it does not mean it's going to happen fast, but it will happen eventually. It also does not mean you don't need to give it a little push, a little activation energy, but it will occur. It's product favored at any conditions. Okay, let's look at the next scenario. So let's say my delta H is positive. Is that good? No, we do not want delta H to be positive. How about delta S being negative? Do we want that? No, neither of those are favored. That's not good. And so both enthalpy and entropy are saying this reaction should not go. That means this reaction is never spontaneous. That means at any conditions, it will not happen without outside intervention. Now, if you give it outside intervention, give it outside force, yes, it could happen. But it's not spontaneous. It will not occur on its own. Okay, let's look at the next scenario. Let's say delta H is negative. Is that favorable? Yes, that's good. How about delta S is negative? No, that's not favored. So now what? It's favored by enthalpy. So in terms of energy, we're distributing energy. That's great. Reaction should go. Nature wants it to happen in terms of energy. But in terms of entropy, in terms of disorder, no, it's becoming more ordered. That's not good in nature. We don't want that to happen. So then what? That means it's sometimes spontaneous. And we're going to come back to this in a few minutes and explain why. But I want you to just in your notes here write that it's spontaneous at low temperatures. So if it's cold, this reaction will go. If it's warm, the reaction will not go. And what warm and cold is, like what temperature is the cutoff, it depends on each reaction. And you can actually calculate what it is. All right, last scenario. Delta H is positive. Is that favored? No, that's endothermic. That's not good. How about delta S is positive? Is that favored? Yes, that's going to more disorder, making a mess. That's great. So now what? Again, if it's favored by one and not the other, that means it's sometimes spontaneous. So again, we'll talk about it in a few minutes, but just write in your notes it's spontaneous at high temperatures. So if it's cold, it's not going to go, but if it's warm, it will go. We'll see why in a minute. So, favored by both, Great, always will happen. Not favored by either. Great, not will never happen. But what if it is favored by one and not the other? Well, what decides? Well, it's the temperature. So how do we figure that out? And what temperature would it be spontaneous or not? So because one driving force agrees and one driving force does not agree that the reaction should go, they had to come up with a different variable, thermodynamic variable, that could kind of tie the two together to see like which one wins. And so they did that, and they called that variable Gibbs free energy. The symbol for Gibbs free energy is delta G, and it's a made-up thermodynamic variable, so you can't go back in the lab and like measure it. It's just made up, and it combines both enthalpy and entropy, and it's used to determine spontaneity. So the equation is delta G is equal to delta H minus T delta S. So Gibbs free energy, that's what helps us determine if it's spontaneous or not, is equal to delta H, which is the enthalpy, minus T, which is temperature, and this temperature has to be in Kelvin. It cannot be in Celsius, it cannot be in Fahrenheit. It basically cannot be negative, that's why. So it has to be Kelvin all the time. And then delta S is your entropy. Turns out, if your delta G is negative, that means the reaction is spontaneous at that temperature. So if you calculate it, it turns out to be negative, and that means with that temperature that you plugged in, that reaction is spontaneous. If your delta G turns out to be positive, that means the reaction is not spontaneous at that temperature. So let's take a look at these reactions here. We want to determine if the following reactions are spontaneous or not. We also want to determine if they are enthalpy or entropy driven. Driven means favored. So are they favored by enthalpy or entropy or neither? Which driving force drives them? Which one is it driven by? And then also, how would an increase in temperature affect the spontaneity of your reaction? So let's take a look at each of these. Let's look at A first. And so to determine this, you want to first look at your delta H and delta S. Let me make it a little smaller. There we go. So let's start with delta H. So is this reaction favored by enthalpy, energy? Yes, it is, because it's negative delta H. So yes. Okay, how about delta S? What do you think? We have 4 particles on this side, 5 particles on that side. That's good. Also, we have liquid and gas mix versus all gases. That's also good. All more random, right? So it is favored by both. So we would say both enthalpy and entropy driven. Both is the answer to the first question. Next, would this reaction be spontaneous? Yes, it would be. It would be spontaneous at all conditions. The last question asks you, what happens if you increase the temperature? Does it make it more spontaneous or less spontaneous? So to do that, to figure this out, let's look at delta G is equal to delta H minus T delta S. So if I were to increase the temperature, because the temperature is multiplied by my delta S, if I increase the temperature, I increase this term that I circled here. And so this term becomes bigger than this term, right? If I increase the temperature. And so if I increase the temperature, I'm basically supporting delta S. I'm saying, oh, I'm going to make the effect of delta S even stronger. And so when you increase the temperature, you look to delta S to see, is it favored or not? If delta S is favored, that means that if I increase the temperature, it becomes even more favored, more spontaneous. If delta S is not favored, then I increase that effect, and so it's even less favored, and so spontaneity would decrease. So in this case, if I increase the temperature, I increase the effect of delta S, which is agreeing that it should go, and so it increases in spontaneity. So if I increase the temperature, I increase the spontaneity. What does that mean? What that means is if I have reactants turning into products, right, and it's a reversible reaction, in a reversible reaction, reactants turn to products, products turn to reactants, right? So at any given point after the reaction is done, I have products, but I also have some reactants left, right? Spontaneous means I have more products than I do reactants at the end. So let's say, at a given temperature, at room temperature, let's say this reaction is spontaneous, 80% of what's left is products. Well, if I increase the temperature, maybe it becomes even more product favor. Maybe instead of 80%, now I have 90% products. So that would make it more spontaneous. That's what that means. Okay, let's look at the next one. We have delta H. My delta H here is positive, and so that is not favored. My delta S, I'm going from 5 particles to only 4. That's not good. I'm also going from all gases, really random, to some gas, some liquid. Not as good. So my delta S, nope, not favored. And so this one we'd say is neither enthalpy nor entropy driven. And so because it's not favored by either, it is non-spontaneous at any temperature. Well, what if I increase my temperature? What's going to happen? Remember we said if I increase my temperature, I increase the effect of delta S. And so we're saying this reaction is not spontaneous, right? So let's say at the end of the reaction, I only have maybe 10% products, 90% reactants, right? That's not good. That's not favored. That's not spontaneous, right? Well, if I increase the temperature, what happens to the spontaneity? Do I make it even less spontaneous? So instead of 10% product, maybe like even 5? Or do I make it more spontaneous, like maybe it's 15 now? It still would be not spontaneous, but there is a degree to that spontaneity, to that product or reactant favored. So let's look again. I increase my temperature, I heighten the effect of the delta S. Delta S is saying, nope, this reaction should not go. So if I increase my temperature, I become even less spontaneous because delta S does not want it to go. And I'm increasing that term right here. Okay, next one. Delta H, negative, that's good, it's favored. Delta S, that's not good, it's not favored. Reason is we're going from gaseous to solid, it's not good. We're also going from 2 particles to 1, that's not good. So in this case, it's favored by enthalpy, not by entropy. So we say this reaction, if it's going to happen, it's going to be driven by the enthalpy. Enthalpy driven. Is it spontaneous? Sometimes. And then if I increase the temperature, what happens? So let's look again. If I increase the temperature, I increase this term, right? Delta H is saying, oh, this reaction should go, it's great. Delta S is saying, this reaction should not happen, right? If I increase my delta S, I'm making this term bigger than this term, so I'm making delta S win. And so delta S is saying, nope, this reaction should not go. So if I increase temperature, this becomes bigger and the reaction is not spontaneous. Decrease the spontaneity. So when will this reaction happen? It's going to happen at low temperatures. Why? Because if I lower the temperature, then I lower this term and delta H wins because it's driven by enthalpy. So looking back at your previous slide, that's what we meant when we wrote it's spontaneous at low temperatures if it is enthalpy driven. Let's look at the last one. Last one, I have delta H. Ooh, it doesn't give me a delta H. I'm going from solid to gas. So in order for a solid to go to a gas, it has to absorb energy, right? So that's endo, that's not good. Let's look at delta S. I'm going from solid to gas. Ooh, from really low disorder to really high disorder, really random gases. So that is favored. Any phase change, just a little tip, any phase change is always going to be favored by one and not the other. That's why we see, all phase changes happen, right? We see water melting or ice melting and then water freezing. That's because it's driven by one and not the other, so it's spontaneous sometimes. It depends on the temperature. So this one we'd say is entropy driven. It's favored by entropy. And it is sometimes spontaneous. If I increase the temperature, what happens to my spontaneity? Well, if I increase the temperature, again, I'm increasing this side, this term. And so delta H is saying in this case, nope, this reaction should not go. Delta S is saying, yep, this reaction should go. If I increase this term, then I'm making delta S win. So the reaction will become spontaneous. So this reaction will be spontaneous at high temperatures. It will not be spontaneous at low temperatures, which makes sense. For a solid to sublimate, turn into a gas, we need to heat it up, have a higher temperature. It would never happen if I'm cooling it and making it at a lower temperature. So I can ask you to do any of these things. One last thing I could ask you is, I could actually give you numbers. These are just the answers that we just went through. I could give you numbers and ask you, hey, why don't you calculate delta G for me? So let's look at this problem right here. It says, calculate Gibbs free energy for the following reaction at 25 Celsius, given that delta H is 28.05 kilojoules and delta S is 108.7 joules per Kelvin. They give us the reaction. They say, is this reaction spontaneous? What would happen to the spontaneity of the temperature increased? So, first thing, to answer whether it's spontaneous or not, I would check, is it driven by entropy or enthalpy? So let's look at this. Delta H positive, oh, that's not good. Delta S positive, oh, that's good. So I can't decide right away whether it's spontaneous or not because it's favored by one and not the other. So I calculate my delta G. Delta G is equal to delta H minus T delta S. Delta H is given to me, 28.05 kilojoules. Temperature, 25 Celsius, but I can't use Celsius. I have to convert it to Kelvin. It's 298 Kelvin. And then delta S, look at this number. Problem is it's joules per Kelvin, but this is kilojoules. I can't do that. I have to convert one or the other. So since I already wrote the delta H, I'm going to convert my delta S. So 0.1087 kilojoules per Kelvin. For the units, this is in kilojoules right here. This is in Kelvin, and then kilojoules per Kelvin. Kelvin and Kelvin cancel. And so I end up with kilojoules minus kilojoules, which ends up in kilojoules. So the units for delta G is kilojoules. Delta G ends up being negative 4.34 kilojoules. So what does that tell us? Is there reaction spontaneous? Yes, spontaneous. Because delta G is negative. What happens if I increase the temperature? Well, you go back to your delta S. Because when I increase my temperature, I'm increasing this right here. And so I increase that term. I make delta S win. Delta S was favored. And so I increase my spontaneity. So this reaction is spontaneous at 25 Celsius and above. If it's below 25 Celsius, we don't know, but at some point it will get cold enough that it will not be spontaneous. All right, this is it for this part of the chapter. Next part, we're going to talk about reaction rate. Have a great day.